Hello, everyone. This is week 2, and this time with sound. Sorry about the lack of sound last time, um, but here we are with sound finally. So, I'm going to go ahead and give the lectures for this week, and as you can see, we have 4 PowerPoints to cover, and we're starting to get into Excel this week as well. So, let's go ahead and get to it. As you can see here, we have an exam guide in here, but don't worry about that exam guide. Your exam's a little bit different. We'll get to it. So I want to get into the shape of distributions for this one, as you can see right here. Different distributions have different shapes. And what is a distribution exactly? Well, a distribution is how your data is spread out. So let's say, I'm going to get my handy dandy pen out here. Let's say that you have a data set, or a data, rather. Let's say we have people. We're talking about people. Okay? People. And person 1 is 19 years old. Person 2 is 20 years old. Person 3 is 22 years old. Person 4 is 21. Person 5 is 21. Person 2 is 22. Person, we're at what, 7 now? Yeah, person 7 is 20. Let's see, how can I, we got 22, 22, 21, 21. We'll make them 20. And then we'll make another person that is 21. Alright, so we have 1, 2, 3, 4, 5, 6, 7, 8 people. So let's go ahead and graph out said people. We'll start with a graph at 19, 20, 21, and 22. And just for symmetry's sake, we'll go with 23. 19, 20, so we'll make another person 23. Easy. So now we're just going to count 1, 2 on the y-axis, 3, 4. So now we have one person that's 19, so we'll go 1, so x 19, y 1, plot that. Now we need a person that's 20, so this, we put another 20. A person that is 22, plot the 22. 21, 21, so we got 2 more people that are 21, so 1, and then we'll add our second for 22. 21 rather. We have a 22-year-old, bam. We have another 20-year-old, go over here and add that. We have a 21-year-old, and then we have a 23-year-old. This will be our distribution. We have plotted, we have 1 19-year-old, 2 20 years old, so on and so forth. Now it's going to actually, we can draw a line across the top of it. And it has a visual distribution of our data set. So different distributions have different shapes. This shape right here is what you call a normal distribution, and we will get to that later, but this is, again, it is normal, pardon the handwriting with the mouse, distribution. A distribution is a group of values that have been organized in some way. Distribution shapes refer to the pattern of a distribution of its scores, that is, how the scores are distributed. And again, this is just how a visualization of that distribution. So let's continue. So the normal distribution, as we just showed in this slide, the normal distribution is not an empirical distribution, one of actual scores, but instead a theoretical distribution, one that is defined mathematically. No real world research conforms to this exactly, so it's going to be hard to get this. mean, it occasionally happens, right? But on the other hand, many approximate for it. For instance, the distribution of physical characteristics of height and weight often do correspond reasonably well. In other words, the average guy I think is like 5'9" or 5'10", something like that. Meaning, you'll have more people here in the 5'9" or 5'10". Average woman I think is around 5'4", 5'5", something like that. You know, and of course, so let's say that we have heights here, and we'll combine these two. Okay, we'll go with the average person, and we'll say the average person ends up being 5'7". You know, so in other words, you'll see more people here at 5'7", peaking the tower, and then you got your 6'10" people over here, and you got your 4'9" people over here. And this will, increase the amount. And height and weight typically average, ends up being a distribution like this. It's probably one of the best examples of a real normal curve, because naturally it's more common for people to be around this height right here than it is for people to be this height or this height. So that would be a normal distribution for height and weight. So let's move forward. Your characteristics of the normal distribution. So let me break this down. We have standard deviations. Okay, this is important, and you need to understand what a standard deviation is. So anyway, don't mind the standard deviation. The first trait of the normal curve is its mean, median, and mode all have the same value. Interesting. So let's go back and take a look at this example I'll put up and back. So what's the mode? Let's see, what number occurs the most? 21, because there's 3 21s in the set. 1, 2, 3. So our mode is 21. Our average, or our mean, which a normal distribution has to have the same median, mean, and average. So our mode is 21. So let's go ahead and quickly calculate our mode, our median, our average. Wow. So let's go ahead and quickly calculate our average. So we got 19 plus 20 plus 22 plus 21 plus 21 plus 22 plus 20. We should have 3 21s. Yes. Plus 21 plus 23. So we got 9 plus 0 is 9, plus 2 is 11, plus 1 is 12, plus 1 is 13, plus 2 is 15, plus 0, plus 1 is 16, plus 3 is 19. 1 plus 1 is 2, 4, 6, 8, 10, 12, 14, 16, 18. 188 divided by, how many numbers are in the set? 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. So quickly plugging that into the calculator, 9 divided by, well, rather it's the other way around. 188 divided by 9. Scratch that out. Don't do math in front of people. It's usually embarrassing. So 188 divided by 9 is 20.8. It's close enough. So that's probably we probably miscalculated one number. So, or maybe my handwriting's too big, but I did add up all in my head. I bet you this total is 190. So let's plug in 190 divided by 9. So 190 divided by 9. No. So what is it really 189 divided by 9? It is. So I miscounted by 1, so the actual sum is 189. So if it is 189, then the total is 21. And our median would be 21. So let's calculate our median real quick. So lining these up in order. 19. I know we only have one 19. 20. We have two 20s. So 19, 20, 20. We got a 21. Mark that off. Another 21. Can mark that off. And another 21. Can mark that off. And now we have two 22s. Sorry for the handwriting. And a 23. Two 22s and a 23. So let's calculate our median. We lined them all up in order. So let's go ahead and cross them out from the outsides going in to get the exact middle of the distribution. One at a time, and look at that, 21. So our average is 21, our mode's 21, our average is 21, and our median is 21. In other words, that's a normal curve. So back to this, 68%, or about 2/3 of the cases, are located within one standard deviation of the mean. So here is 68% right here, and this box represents 68% of all people in our height case, in our height example. In other words, 68% of people are probably between the heights of 5'5" and 5'10", or maybe even 5'11", right? And then, so this is what's known as the zero standard deviation. So they're within one standard deviation of the mean. This is where the first standard deviation begins. This is where that is. So this box is within one standard deviation of the mean, which is right here. This is where the mean's at. It's on 0. Alright. It is symmetric. That is, left and right sides are mirror images. Yeah, this looks pretty mirror images to me. So this would be a normal distribution. Keep that in mind. Okay. Now, you're almost never going to get this unless you're talking about like a very large sample size. And of course, you know, common thing that's, you know, you call it. But yeah, that's your normal distribution. We will move forward. Skewness. This is skewness. Modest positive skew, moderate positive skew, strong positive skew, and extreme positive skew. So, you know, and then we have the income right here. And let's get to the text behind this. Skewness refers to how distributions shape depart from symmetry. The more the departure, the greater the skew. So a positive skew, then, is scores cluster at the negative end. Well, why is it called a positive skew if it clusters at the negative end? Well, it's called a positive skew because the tail is on the positive end. So wherever the tail of the distribution is, that's the kind of skew it is. So as you can see here, the tail is way over here. You know where the tail of it is on the positive part. So remember, positive skew, positive tail, negative skew, negative tail. And this means the distributions are lopsided. In other words, take a look at income in the United States. Okay, most people in the United States make $100,000 or less, whereas you have a lot of people, very few people make $1 million or maybe even more. So this is rich. This is normal. And as you can see, most of the people make less than $100,000. So with income, you will never calculate income with the mean. Instead, you will use the median to calculate income. It will give you a better idea of what's going on. All right, moving forward. Negative skew. Scores clustered in the positive side of the distribution. Again, negative skew means negative tail. So the tail's on the negative side, on the left side, which is the negative side. So we will now look at that. So what's a good example of negative skew? Gestation, or how long a person's pregnant before they give birth. So sometimes the baby comes out at 5 months. Sometimes the baby stays as long as 10 months. But most of the time, they come out around 9 months. You know? So, in other words, scores cluster on the positive side, but the tail, as you can see, this is the tail, is on the negative, and that is your negative skew. Kurtosis is how peaked a distribution is. So the more of a squeeze you got here, so, this is like pinching. If it pinches really bad, it's got high kurtosis. If it doesn't pinch nearly as bad, it's got normal kurtosis. And if it looks like a little knob, low kurtosis. And that is just meaning you got more people or things or whatever you're measuring stacked right in that middle. Kurtosis is the degree of peakedness. This is just something like a bonus. We're not talking about too much about kurtosis in this class, but moving forward. Z-scores. We're not going to get into Z-scores too much, but it's also something that you need to know. A case's Z-scores, which is a number of standard deviations that the case's score value is above or below the mean. For instance, if Alice's score on the self-esteem scale is 2 to standard deviation below the mean, her Z-score is -2. To compute a case's Z-score, subtract the mean from the score and divide by the standard deviation, where Z is the score for the case, X is the score for the case, and X crossbar is the mean score, and S is the standard deviation. So what would a standard deviation of 2 look like on this scale? Well, your standard deviation of -2 would go exactly right here. Okay? Meaning Alice, in this case, is very unusual. She would place on the -2, meaning she's quite rare in that she is, in this case, one of the bottom 5% performers. What was she performing -5% in? Self-esteem, meaning Alice has very low self-esteem. So for all variables, scores below the mean have negative z-scores. Scores above the mean have positive z-scores, and scores exactly at the mean have a z-score of 0. Researchers use z-scores to assess a case's relative standing on different variables. That is your z-scores. Now, review time. I'll open up the exam and go over it. It's not a big deal. We're going to, because the format's a bit different in the summer classes, because I got to cram all this stuff in at once. So that is that slide. Let's move on to the next. We're going to look at measures of dispersion next. And I know I skipped over one. I skipped over one because it makes more sense to skip over that one for now. And this is not opening up because PowerPoint. Here we go. That's not it. Here we go. Measures of dispersion, or variability, whichever way you want to put it. Let's move forward. Measures of variability describe the variety, diversity, or heterogeneity of a distribution of scores. Variability then refers to the degree to which a variable's values are dispersed around a measure of central tendency. And measures of variability are useful for measuring consistency of performance, for example. For example, while evaluating an ambulance response time of 2 different services, both average response times came out to be an average of 7.4 minutes. Now let's compare service A versus service B. Now I want you to think back to, let me get a drink here. Think back. Ooh. My voice squeaked. 36-year-olds, my voice just squeaked. Okay. Let's start over. I want you to think back to the money example, where I said you should not use money as average for your measure of money. Well, these measures of variability will show you exactly what's going on. So let's look at the ambulance response times of of service A versus service B. You can see here the two times are different. So we have one. Remember, they both have the same average. Let's go back and take a look. They both average out to be 7.4 minutes. So let me get my marker going here. And so we have 7.4 minutes right here as our average, and we also have 7.4 minutes right here as our average. Notice how these are distributed. As you know, as I showed you in the previous lesson, this means there are very few 0-minute response times, and this also means there are very few 14-minute response times. But over here, we have plenties, well, not plenties, but more, 0 minutes and 14-minute response times. Where it really gets different is there are very few 4-minute response times, but there's quite a bit, like literally, like almost 150. Whereas there's about 30 over here. All right. Now, let's get to the average for, here. We have roughly 175 7.4 minute response times, whereas this graph has about a little over 300 7.4 responses. That means these are vastly different data sets. But you can average up different numbers. You can add up a bunch of different numbers to get the same average. That's basically what this principle is saying. So, ambulance service A here versus ambulance service B here. Ambulance service A rarely has a 14-minute response time, and it rarely has a 0-minute response time. More commonly, you'll see ambulance service A respond within 4 to 10 minutes, where it's much more common for this ambulance service to go anywhere from 2 to 12 minutes. In other words, this service is more inconsistent. It varies greatly, whereas ambulance service A is far more consistent. So variability measures consistency. Service A indicates less dispersion, so this is less dispersion right here. Service B indicates more dispersion, and dispersion is variability. That's another word for variability. The peak of dispersion is called kurtosis, which we went ahead. And remember how I said this is more pinched? The more peak it, or the more kurtosis you see in a data set, the more consistent that data set is. Service A has a higher level of kurtosis than service B. And as you see, this is true because this is more pinched together. It's got a higher peak. This is less pinched together and has a more rounded peak. More consistent is A, and B is less consistent. So your range, so we're going to get more formulas here. We're going to learn some more stats. Your range is your high score minus your low score. Easy enough. So let's say we have our high score of 15, for example, and our lowest score is 9. Our range is equal to, simple enough, 15 minus 9, which is 6. Range will be 6. Where it's we have more consistent data. 13 is our low score and 15 is our high score, then our range would be 2. Or negative 2 in this case. Well, no. Yeah. High score minus low score, so it would be 15 minus 3, 13. Equals 2. And the lower your range, you can expect more consistency. Now, we don't use the range for anything, really, except for modes. Except for nominal data. You will use range on nominal level data if you cannot IQV it. And we'll get into nominal data eventually. So don't depend on this. And the range is a great way to show the first. And you probably learned the range in middle school, right? Maybe even less. So this is just a way to measure variability. So your interquartile range is more accurate, but still very limited. This is the distance from the third and the first quartile of the distribution. So interquartile range is Q3 minus Q1, or 25% of where the 25th percentile is. Okay? The 75th percentile minus the 25th percentile. Now, consider this. The median, as you know, is your 50th percentile, or it's our Q2. So, that being said, 25, 50, 75. Okay? This is 1, this is 2, this is 3, and then, we got 100 and 0. Okay? So, 4 and 0. So, This is the distribution. So what you're doing here is you're taking this the 75th score, subtracting it from the 25th score, and that would be your interquartile range. So let's say that our 75th percentile in this case would be, we'll say 37. And our 25th percentile is 13. We would do 37 minus 13. That would equal, what do I pick hard numbers? 24. Mental math. Anyway. So steps to find the interquartile range. Remember that I said the median is the 50th percentile. It's the same deal as finding the median. You arrange your cases in order. You find that case that lies between the numbers by multiplying n by 0.25. Find the case that lies at the third quartile by multiplying n by 0.75, or 3/4. Subtract the score of Q1 from the Q3, and this is our interquartile range. Okay. Okay. So let's move forward. The mean deviation. Alright, I'm going to do this in Excel, and I got a bunch of other Excel stuff to do for you. So let me get into Excel real quick. Opening Excel. Hopefully you can see Excel. So let's go ahead and do this in Excel. So let's say that we have a distribution of 5, 4, 7, 8, 9, 2, 5, 4, 8, 5, 4, 6, 8, 5. We'll go one more. 1. Alright, this is our distribution. So, in order to find the mean deviation conveys the average amount by which the values differ from the mean. First, we're going to find the mean, and I will zoom in on this. Oops. Zoom in so you can see what I'm doing here. So we're going to find the mean first. So I'm just going to go ahead and make a very clear, visible line so that you can tell where the calculations start. So in order to find the mean, we hit equal average. Highlight the entire thing. Hit enter. And this is our average for the distribution, 5.2667. So we have the mean now. For each case, we subtract the mean from the case's value to determine the deviation score. So for each case, we will subtract the mean from the case's value. So in other words, 5 minus 5.2. In order to do this quickly, we can equal 5 minus 5.2. And this is the quick calculation for Excel. Now let's say that we want to do this quickly because we're lazy, and statisticians are, historically lazy. We would have to find, for each case, subtract the mean from the case's value score to determine the deviation score. Again, subtract the mean from the case's value score. So equal case number, which is 4, minus the mean. Now, in order to hold the mean constant and to make sure that we can do it all the way, I'll show you real quick what happens if we just drag it down. As you can see here, we just get, the cases score. But what if there was a way that we didn't have to deal with that? Well, you're in luck because there is a way. In order to hold things constant in Excel, we add a $sign to lock the A column and a $sign to lock the 17th row. In other words, when we drag it down, we're telling Excel, oh hey, don't drag that down. So we now reevaluate this, and then bam, look at that. So nice. So all the way down, you can see that it held this constant. So what this is, let me add a row up here. Insert. This is our deviation score. And this is our cases. Case. So now we got to find the absolute value of each deviation score. To quickly find the absolute value, we just, create the positive version of each number. So 0.26667, 1.2667, and then any positive score we can just copy right on over. So hit that, drag it down, enter. Keeping this simple for now, or at least relatively simple. And then 0.2667, 1.2667, 4.2667. A lot of 0.667s here, huh? 3.2667. 1.2667. 0.26667. 1.26667. So this is the absolute value for the deviation scores. So we'll just put absolute value there. Go ahead and widen these out so you can see what's going on. Then you sum these absolute values. So we're just going to go down here, equals sum. This, highlight everything, enter, it adds them all up, no problem. And then divide this by our sample size. So we need to find our sample size. So let's see, here's our sample. Equal count. And we're just highlight this, enter. Our sample size is 15. So this would mean, our mean deviation is the sum of the absolute values divided by sample size. And our mean deviation is 1.786671. That is how you do it. This is recorded so you can go back and reference this. And now we can go back into the PowerPoint. So mean deviation example, I kind of broke it down for you right here. You can go ahead and check that out. On the PowerPoint, look at the video, reference that video. Standard deviation and variance, gold standard. Standard deviation is how close your scores are far from the mean. First you find the mean, then you subtract each case from the mean to determine this case's deviation score. Same thing as the mean deviation so far, but except this time you square each deviation, and then you sum the squared deviation scores. Finally, you divide you divide the sum of the squared deviation scores by n minus 1. This is variance. Then you calculate the square root, but we're not going to do that. Instead, what we're going to do is we're going to go to Excel once again, and we're just going to do equal std, calculate standard deviation based on the entire population given as arguments, estimate standard deviation based on sample, estimate standard deviation based on sample including logical values and text, calculate standard deviation based on entire population including logical values and text. The function is available for Excel. So what we're going to do is standard deviation P, which is the entire population, not a sample. So STDVP, just click on it, and we're just going to highlight everything and enter, and there's our standard deviation, no problem. Remember, that is standard deviation P. Standard deviation P. Anyway, IQV. we will have a whole class on IQV. Okay? So IQV is a nominal level measured, and we'll get to the nominal levels when we get there. This is a ratio amount of variation observed in distribution scores. The IQV score ranges from 0 to 1. Racial diversity in the U.S. will be a good statistic to use this with, and the population only included white folks, then the IQV score will be 0. Remember I said earlier that nominal data in the first lesson, or at least in the first slide, is that nominal level data is things like eye color, race, gender, things that you can't really add ranking value to. Okay? So the only way we can really do stats with this is calculate the mode, or we could use IQV. Now what IQV does is it just says, oh, this is a diversity score. If the IQV score is 1, then it's a very diverse data set. If the IQV score is 0, then it has no diversity. Or in this example, if you had a sample size of 100 people and they were all white, then your IQV score would be 0, representing no diversity. Pretty simple. Here's your IQV formula. I will give you an Excel sheet that I pre-made that you can access on your own without having to do this mess. So let's say the racial makeup for the U.S. is as follows. F is already in percentages. Non-Hispanic, white, black, Native American, Asian American, Hispanic are your nominal categories. So 71, 12, this is how many people are there. So you got 71 non-Hispanic white, 12 black, 1 Native American, 4 Asian American, and 12 Hispanic, which is a total of 100. So it's just kind of doing the sum of squared frequencies there. But, you know, that's just how you would do that. But I'm just going to give you a page, an Excel page, so you can calculate it automatically and don't have to worry about it too much. Alright, cool. Now we have to make it to the next bit of content. So now we have shape of distribution, Excel and percent change, measures of dispersion. We're going to hit up Excel and percent change now. This gets into ethics a little bit. And before we start into our research segments, I want to talk about Principle 1. You want to minimize the risk of harm. Principle 2, obtaining informed consent. Before you give anyone a survey, you got to make sure people know what they're signing, know what people are getting into. And you got to make sure that they can leave at any time they want to. You're not trapping people with a contract. Principle 3 is protecting anonymity and confidentiality. Principle 4 is avoiding deceptive practices. And Principle 5 is providing the right to withdraw. Now, as part of your homework, I want you to watch the syphilis experiment, and I want you to watch the Milgram study. There will be questions on this later, so make sure you watch this. So for statistical programs, we make our job easier by a ton. Some programs that you may use include Excel, SPSS, Stata, R, M+, SAS, and so on. Today we're mostly watching videos. Again, it was earlier. But it seems to be the best way to go about this. Each slide will read you the formula plus a link to the click so that you can access a how-to anytime that you need it. So for percent change, this is percent change. Delta means difference, by the way, and delta is that triangle. This is delta. Oops. Let me get my ink pen out. So this is delta, which means the difference of V in this case, okay? Percent change equals the change in value divided by the absolute value of the original value multiplied by 100. From 10 apples to 20 apples is a 100% increase in the number of apples. Okay, so let's say that we have V, difference of V divided by absolute value of V, first variable, times 100. So, okay, so we have 20 apples, okay, from 10 apples to 20 apples. Okay, so let's say year 1, we had 10 apples. And the next time we harvest it, in year 2, so our year 2 harvest yielded 20 apples. What's the percent change? What's 100%? So let's go ahead and calculate this out. So we put our year 2 first. So year 2, 20, minus our year 1, 10, divided by the absolute value of year 1, which is 10. Cool. This is how we do it. So we do this, 20 minus 10 divided by absolute value of 10 times 100. And of course, we have our times 100. Equals, so 20 minus 10 is, of course, 10 divided by 10 times 100. This equals 1 times 100, which gives us a 100% change. In other words, our apples doubled. Simple enough. Percent change in Excel. First, you type an equal. Let me get into Excel here. Let's go ahead and start another book. And zoom this bad boy in. Take a drink. So, percent change in Excel. Let's get our year 1 and year 2 data real quick. Year 1, we'll say 8. We'll say ice cream cones sold. And on year 2, at the end of summer, we sold 15 million ice cream cones versus 8 million ice cream cones. Okay? 8 million versus 15 million. So in order to calculate this, first we hit equal. Okay. Then type this, make a frowny face, click the box of your new value, which is your year 2 value. Hit the minus key. Click the box of your old value, or your year 1 value. Click the box of your old value. Again, I got that. So we close our parentheses now. Okay. Hit the divide key. Click the box of your old value again. Sweet. Hit enter. Then we convert this into a percent. Up here, under the home tab, it says percentage. And look at that, 88% change. That's pretty accurate. So we had an 80% change, a positive 88% change in sales. Now, there's a slight variation here. Sometimes your old value might be negative. And if it is negative, make sure you just absolute value that before you shove that formula in there. So that is, and you can watch a YouTube video that I have linked here to check that out too for percent change. So we're going to move forward. Frequency tables. You can watch these tutorials on frequency tables. Go ahead and check that out. For rates, let's calculate rates. Alright. So, let's get into rates. So for rates, we're making another sheet. Zoom this sucker in. So, type in, let's go with crime, okay? So we're going to go with murder. Murder. Okay. And we'll say, let's make a little data set. It's going to insert columns. Insert columns. Insert columns. So for rates, you need what year it is, the population of the area, and of course, the crime you're calculating, or whatever you're calculating, really. In this case, we're talking about crime rates, so we're talking about the murder rates. So let's say, just to keep track of things, we're just going to insert another column and say location. Okay, so we'll say Louisville versus Lexington versus Bowling Green. 3 places, 3 whole places. We're just going to go with the year 2000 because it's easy to type. So, and we'll make up populations because, we just need to make up numbers. So 500,000, 525 for Louisville. For Lexington, we'll go a little less, so 210,534. And for Bowling Green, we'll say 80,579. Okay. So there's our population for each respective places. Now, just to illustrate rates and why it's important, I'm going to put an imaginary number here, and I'm going to say each place had 234 murders. Okay? Now, this would make Bowling Green the most dangerous place out of all these three areas because of the rates. So let's make another column called rate. Okay, to find our rates, first we will make a third column, and this is our fifth column for this case, and title it crime rates per 1,000. We just title it rate. Okay, but this is our crime rate. Actually, let's make this crystal clear and put in crime rate. Alright, cool. First, and then you go to the blank column and you type your frowny face in to get things started. We always start our exercises off with a frown. Then click your crime column, so our murder column, 234. Divide by your population. Then you close your parentheses, and then you multiply by 100,000. Alright? And because we just need to do it one time, and we don't need to hold any numbers constant, we can just drag it down. And as you can see here, Bowling Green indeed does have the highest crime rate of 290 murders per person. Okay, this place has 111 murders per 100,000 people, and not per person, per 100,000 people. And it's per 100,000 people because we multiplied by 100,000. Now, if we want to do per 10,000, we could just take off a zero here, and then suddenly that's per 10,000 people. So let's say we want to do per 10,000 people. As you can see, it gets a lot smaller because it is per 10,000 people. So Louisville has 4 murders per 10,000 people. This place has 11 murders per 10,000 people. This place has 29 murders per 10,000 people. Now, just for the sake of consistency, we're going to bump it back up to 100,000 because most of the time you're going to be doing stats in per 100,000 populations. So again, Louisville has 46. This is not true. This is not true data. I just made this up. Louisville, in this example, has 46.75 murders per 100,000 people. Lexington has 111 murders per 100,000 people. And Bowling Green has 290 murders per 100,000 people. And what this rate stat does is it controls for your population. Because what really happens is the bigger the place is, the more murders happen in it. And you don't want the bigger the place is being the primary predictor for murder, because it does not really necessarily measure safety. Louisville is huge compared to Bowling Green. Okay, more people are here, there's more space here, more stuff's going to happen, and that's just the way it is. So that is rates. An easy way to do fill-in reminders, and I just showed you how to do that. If you really want to do it manually, here's a way to do it. And this is how you enable that drag and drop. You can refer to this to get that done. Finding the mode in Excel. Alright, let's go ahead and find the mode. Now I'm just going to operate off a single data set now. 10, 9, 8, 8, 8, 5, 6, 3, 2, 1. Okay. In order to find the mode, we're just going to do simple equal mode. See that little triangle there? Highlight that. Done. Their mode's at 8. And see, 8 took place the most. That is finished. So let's move forward. Finding the median. Same deal. Equal median. Oops. Equal median. Click on it down here. Drag. Like so. Enter. Our median is 7. Finding the mean. Same deal. Equal mean. Equal average. My bad. I've been working in another program. Equal average. There's your mean. Creating graphs. Enter your data into Excel. Highlight all the data. Choose one graph to charts, the option to make it. So let's say we want to graph our crime data. Okay. So let's just go here. Insert. Chart. Where are you at? We can just go to recommended charts. We can do a little bar chart. And there we go. That is showing you the crime, well, the population, the population in Louisville. Okay. So let's say that we want to let's go ahead and delete this. We're just going to insert another one, highlight it, insert, chart. We're just going to go to all charts here. Let's take a look at pi. Now if we want to do a chart with a population, what we need to do, we're just going to highlight our crime rates, insert, pie chart. We have our crime rates in the areas. Okay. So there is the way to insert charts in all that nice places. So oops, we got a reference. But that is how I do the charts. And then IQV, I'll give you a sheet to do IQV. Calculating range. I showed you how to calculate range already. Interquartile range, I already showed you that and previously in the exercise. And standard deviation, I showed you how to do that already. But we'll go ahead and refresh standard deviation real quick. If we want to find standard deviation, you just type in equal stdev p, highlight the whole data set, enter, and there's your standard deviation. And that covers that. Alright, moving forward. Okay, so that would be course content, week 2, survey design. So with survey design, we're going to hit this up. I'm not too concerned with survey design for the summer class. This is just something for you. I'm not going to have you do a survey, so I'm not going to go over it. Read up on it to get to understanding surveys. But this is just material. Take a look at it. Because we don't have the time to do a survey in this class, so I'm not going to assign a survey in this class. But you know, it's interesting stuff. Take a look at it. This leaves us with the assignments, which I'm going to look at now. Assignment, project 2. Go ahead and download that sucker. Draw the Wheel of Science. This can be found in the first PowerPoint slide in Introduction, the Walter Wallace's Wheel of Science. Go ahead and just draw that out. What's the difference between qualitative research and quantitative research? That's also in the first point of slides. What's the difference between descriptive and inferential statistics? Also in the first set of slides. Describe the following. Normal distribution, I went over that today. Skew, I went over that today. Kurtosis, I went over that today. And then draw a normal distribution, and I define standard deviations. Remember that standard deviations, like the first standard deviation is the 68% of all the data. If you recall right, I did draw around that. Go ahead and refer to that if you need help with that. List the type of questions you should avoid asking on surveys. Just take a look at the PowerPoint on surveys. It will give you those. Alright. And this leads us to our exam. Let's go ahead and take a look at our exam. It is an Excel sheet. Okay. So here is your exam. For this project, complete the following tasks using Excel formulas. Find the mean, the median, and the mode for all variables of the dataset. Find the standard deviation for all variables, and find the mean deviation for all variables. So here's your data. What I mean by variables is age is a variable, height is a variable, weight is a variable, and test score is a variable. Now here is a really cool pro tip for this. Let's say that we want to find, oh, I need to hit enable editing. Let me zoom in on this. So I'm just going to go down here and say mean. Actually, I'm going to make things a little bit less confusing. I'm going to make an entire different row here. So insert one row. And I'm going to say mean, median, mode, standard deviation. Okay. And I'm going to hit equal, average, highlight this entire thing. Cool. We got the average for age. Our average age in today's set's 22. Equal median. (22) equal mode. And equal standard deviation P. Now check this out. We can just take this whole thing and highlight it and then drag it over. Ba-bam. And that does everything for you. Look at that. That answered literally every question on here except for find the mean deviation. Now, I'll leave that to your own to figure out. Refer to the video I'm recording right now. And remember to do that for every variable, which means you need to do the mean deviation for age, height, weight, and test score. And then report that right here. Mean deviation. Alright. I'll leave you to that. And that is it for this week. Thank you.